invitation to your and thank you very much for your invitation to your seminar, to online seminar. Yeah, so I was planning to talk today about suspensions of particles in fluids, which are actually very rich systems with very rich properties that have been that have attracted a lot of interest recently in the mathematics community also. And what I will be discussing is mainly based on some joint work with Antoine Gloria. All right, so let me just start with describing the system that I will be considering. So I have I consider, let's say, a large domain, a large box. I mean, we don't really care about the boundary condition in that box. And we fill it with a certain fluid, a viscous fluid, and then I put in suspension in the fluid a large number of small particles, small rigid particles. So the regime that I will be interested in is really the collective regime, when you have a very large number of very small particles. So n will be the number of particles, very large, and epsilon will be the size of particles. And yes, and just for simplicity, as in the picture here, I always consider like just spherical particles, but I mean, you should just remember that it really doesn't matter any size, random size, or anything could do. I mean, you could still do the analysis. Just for simplicity of notation, I take sphere. So you'd like, of course, to write down equations for these systems, first of all. So maybe you might want to write down, let's say, Navier-Stokes equations for the fluid. Then you put, let's say, no slip boundary conditions at the boundary of the particles, and then you just write down Newton's equations for the particles. This is actually super complicated if you take Newton plus Navier-Stokes. So first of all, we should simplify a little bit the problem, otherwise we can't say essentially anything. And what is quite natural is to first of all to neglect the inertia of the particles, and to say that, well, that you just look at the Stokes fluid, so you no longer have Navier-Stokes, but just Stokes equations for the fluid, and then for the particles you also neglect the inertia, and so you just replace Newton's equation by just equations that say that the particles move with the fluid essentially. So let me just write down equations for that system that we will be considering. Oh, I should move that bar, otherwise I don't see anything. All right, so so I just write down first the equations for the fluid. So if you have if the position of the different particles are given and a given instant of time, so I denote them by b epsilon n. That's my the different particles. And so now in the fluid domain, so in u minus the particle, I just write down the Stokes equation that you see here. So minus Laplacian of the fluid velocity plus rho of pressure is equal to, well, to some h, which is just like some internal force that I take into account. Then, of course, you are incompressible, your divergence is 0. And then you need to put, as I was saying, you want to put no slip boundary conditions. So it means that at the boundary of each particle, you would like the fluid velocity to coincide with the velocity of the particle. So at the boundary of each particle, u should just be some rigid motion, because the particles are rigid. So they just have like a translation velocity and rotational velocity. So this is what I write here. So u should be of this kind of form on the boundary of each particle. Well, so here for the notation, I will always extend u also inside the particle. So actually, I assume that u in the particle is equal to that field, to that rigid field. So it means that inside the particles, the symmetric gradient of u vanishes. So between notation, but just think that you put that as a boundary condition. And then, well, you start with Newton's equations, but now I just want to neglect inertia. So what I still have is the balance of forces and balance of torques, which are natural boundary conditions also, which I write on here. So I don't want to go too much into the details of the form of those terms, but so this term here, this boundary integral, you should understand that it's just like the force which is exerted by the fluid on particle number n. And so sigma is just the Cauchy stress tensor, which I write on here. It doesn't really matter the precise form, but anyways. And so here I also consider another force. So I have, of course, an internal force H, but I also consider a possible sedimentation force, which is acting on each particle in direction of gravity. And this is just like the balance of torques, which is also natural to consider. Well, so now from this system, you can check that actually, if you give yourself the particle position at the end, you can solve this equation. There is a unique solution for the fluid velocity. In particular, you deduce the value of v and theta. You deduce the velocity of each particle and the angular velocity of each particle just by solving this system. And then you can just update the particle position, and the particle dynamics is just given by this dtxn is just vn. that is computed from this system. So you see, it's a kind of a quasi-static equation where for given position, you just solve the fluid equation. It gives you velocities, and then you can update the particle dynamics. I would just like to emphasize that this equation is, so it's quite, in fact, it's quite rich and kind of complicated. I'd just like to emphasize on two things, which are that, which is about the nature of those interactions. So of course, you see that the different particles, they interact via the fluid, because dTxn is Vn, which is given by solving these equations. And those hydrodynamic interactions, you see that they are multi-body, which is something very important, which is that indeed, in order to get Vn, you need to solve the full equation here. And you see that all particles are appearing at the same time in those equations as boundary conditions. So it means that Vn is not just like a sum of pairwise interactions. It's really Vn is a function of all the other positions at the same time. So it's really multi-body in nature, which is something very important, which will be part of the difficulty in the sequel. And this is really related to the fact that you have particles which are not just point particles. It's really particles which take a certain space. And then the other thing is that you have long-range interactions, which will also be a difficulty in the sequel. So if you look at the influence of a particle at a given point of space, in fact, it's really changing the fluid very far, and the decay is quite slow, and this will be, of course, a part of the problem. So first of all, what do we actually want to prove? What is the goal in this setting? Well, the ultimate goal is to understand the large-scale rheology of such systems, to understand on large scale how this fluid with the suspension is behaving. Typically, you expect to have some kind of effective fluid description. On large scale, I mean, the suspension just modifies a bit the behavior of your fluid. You have an effective fluid. Typically, you would like to understand the effective viscosity, which is one of the properties of this kind of effective fluid. What you expect, of course, is that because you have those rigid particles, the rigid particles somehow hinder the fluid flow. So you should somehow increase a little bit the viscosity and get a larger effective viscosity. Of course, this effective viscosity will depend on the whole microstructure. But, it's some kind of homogenization problem. So given all your position, you will given your microstructure, this will be somehow averaged, and you expect to define some notion of effective viscosity on that scale. But you see that the difficulty is that you don't just have an homogenization problem. The thing is that it's a dynamic problem. So also the microstructure is actually evolving. And this is very interesting, because then if you put a strain if you apply a strain to the system, then you know that all the particles will move, and all the microstructure can somehow adapt dynamically to the strain that you apply. And in the end, you see that the effective viscosity will depend on this microstructure. And so you see that you have some kind of nonlinear a response, and so typically you expect to have naturally some non-Newtonian effects. But it's quite complicated, because it really involves to couple some kind of homogenization, this notion of effective viscosity, to this evolution of a microstructure. And this is like the ultimate goal, but we are still very far from understanding this kind of evolution. So at the moment, I will mainly focus just on the first part, and of course, the goal is then to couple to the microstructure, but the result I will show you are still not as evolved as that. So let me just tell you a bit of what has been done and the regime that we will be considering. So what has been done in the past mainly is to look at the dilute regime. So when the volume fraction, lambda will be my volume fraction, so that the volume fraction of particles. So when lambda is very small, so it means you have very few particles, they are very sparse. They're kind of isolated. You can view them as being like isolated from one another. And I mean, in that regime, in fact, essentially the microstructure plays no role to leading order. And you can just prove some kind of mean field result, which is what people have been very interested in, which is just like looking at the density of particles and just looking how it evolves. So this is interesting, but however, in this kind of dilute regime, you see that the rheology does not change. The effective viscosity of the fluid remains the same. So there is no correction. So it's not extremely interesting, because in particular, I mean, if the microstructure plays no role, there is no possible non-Newtonian effect. So, I mean, the real goal is, I mean, you're really not dealing with it. So, of course, what I would be more interested in is to really to see the microstructure and to see its effects. And so for simplicity, of course, you first want to consider just some kind of I would call it an equilibrium regime, where I just forget about the evolution of the microstructure. So I just assume that the microstructure is given. You have a certain law for the microstructure. You have like a statistical ensemble of positions, And then you want to define the corresponding effective viscosity and study it, right? So this is like just the third part that then you should couple with evolution, but this is something we still can't do. Right, so this is then really just a homogenization problem. You fix the microstructure, you want to understand, given the microstructure, you want to understand what is the large-scale behavior, the large-scale, define a notion of large-scale viscosity. And as you see, because the goal in the end would be to couple this with evolution of the microstructure, it means that you really want to get a homogenization result, but under the weakest possible assumptions on the microstructure. It's very important to have very weak assumption on microstructure because under the evolution, you don't have a lot of information. So this will be our goal, one of our goals here. So to describe some homogenization result, the most general possible homogenization results in this setting. And well, then, of course, it will be about a coupling in the second step. That will be about coupling with the evolution of microstructure. But of course, this is quite complicated, and it's kind of natural to go back then to a dilute regime where you simplify a little bit the situation. So, so to go to a dilute regime and to look then at this effective viscosity that we just defined, and you would like to try to make some asymptotic expansion in the small parameter lambda, which is the dilution parameter, the volume fraction. So this is the kind of asymptotic expansion that has been done and has been considered by many people in fluid mechanics. But what is very interesting is that, of course, the leading order, you just have like the viscosity of the plane fluid. This is what was considered when doing like mean field limits in this first type of result. You just replace, you just have like the viscosity of the plane fluid identity here. But then if you consider corrections, you see that, of course, corrections will involve the microstructure, but just in a simplified way. So you not need like the full information of microstructure, but just like some reduced information on the microstructure. And then, of course, this is something which might be easier to couple, I mean, to study the dynamics. So if you just truncate at like the first two terms of this expansion, and then you just try to understand the evolution of that one, it's of course much simpler. So, I mean, again, the long-term goal is to go to the dynamics and to try to couple all this in a certain regime to the dynamics, which we can't do at the moment. So at the moment, I will just talk about two things. So first, the precise definition of this effective viscosity in this kind of equilibrium setting. And then I will talk about how to make such kind of dilute expansion of the effective viscosity. And we have somehow also here now a complete picture of how to proceed. All right, so this is then the plan for today. Okay, so let me start with just recalling you the setting, the equations now in our equilibrium setting. So now we just fix ourselves a statistical ensemble of particle positions. So we have a point process Xn. Of course, you want to have small particles of size epsilon. So let me rescale everything. So now the centers of the particles will be just at the epsilon Xn in the domain. And I again just consider like small balls of size epsilon on those points. And then my equations are just, as I said, so my Stokes equation in the fluid domain. And then I have my rigidity constraint, and I have the balance of force and torques. And again, you have two sources of forces. So one is just internal force H, another one is some kind of sedimentation. Okay, so maybe before we start the homogenization, I'd just like to emphasize that those equations, I mean, they might look a bit complicated. There are many boundary data. I just would like to emphasize that it's all the conditions, the boundary conditions are actually natural. It's just about rigidity constraints actually. So for that, let me just emphasize what is the form of the weak formulation, so that you really feel like very comfortable with those equations. So you just test the equation with a test function W, which satisfies the constraint. So it's incompressible and it's rigid inside the particles. Then it's a direct computation to see that all the boundary conditions are just made so that the weak formulation takes this form. So you have just the Dirichlet form on the whole domain, which is equal to then simply your test function against some kind of, as you see, some kind of effective internal force, which takes into account both the true internal force H in the fluid domain, and also exactly on the same footing, you get the sedimentation form E inside the particle. So it's like very simple kind of weak formulation, where you see that, I mean, in fact, this is just like the weak formulation of the usual Stokes equation that would be posed in the whole domain with these red terms as your internal force. The only difference is that now you ask that u epsilon and also the test function be rigid in the particle. So if you like, you can also view then those equations a bit differently by saying that, well, u epsilon is just like a projection of v epsilon, where v epsilon would be the solution of this Stokes equation on the whole domain with this effective internal force. And then you just project it with pi epsilon, which is just the orthogonal projection on the subset that satisfies the constraint. I mean, that's a direct consequence of this weak formulation. I just like to emphasize on one thing, which is that I include here some sedimentation force. I just like emphasize that this is a little bit of cheating. So if you just look at scalings, you see that this is a boundary term. So this should be epsilon d minus 1. And I put a sedimentation force, which is a volumic term. So you see that at the level of scaling, this is not quite natural. So if you would like actually to consider a sedimentation problem, this would be about putting here epsilon d minus 1, which would mean that in the weak formulation, you would have a factor 1 over epsilon in front of the e. So in fact, if you consider a true sedimentation problem, you pump a diverging amount of energy in the system. So it's a completely different story. And I mean, this is also something you can study and that I have been studying, but the whole result is completely different and the questions are really radically different. I don't want to talk about that today. So here, when I talk about sedimentation, it's really some kind of very weak sedimentation force, which is clearly subcritical in terms of scaling. All right. Oh yeah, and I was just mentioning a last thing that, of course, if you like, you can always think about those equations by saying that, well, this is just about looking at Stokes equations in the whole domain. Well, now I put a viscosity, which I put as being diverging. So I have a viscosity theta inside the particles. When I let theta go to infinity, you get back exactly, of course, your equation. So this rigidity constraint, you can also always view that as just being like the viscosity being infinite inside the particles. And this is the usual thing. Okay, so this is about then our equation. So now let's turn to the homogenization results, to defining well, the effective viscosity as we want. And so let me just try to state what should be a theorem, a homogenization theorem. Let me tell you the different things here. So of course, you epsilon, the fluid velocity is bounded in H1. So you expect this to converge weakly in H1 to something, and to some u bar that should be correspond to some kind of effective fluid velocity. We should then satisfy a corresponding Stokes equation as I write here. So of course, the force, the internal force that you should have at the limit is just the weak limit of the internal force we had before. So it was h outside the particle and e inside the particle. So when you take the weak limit, you have a 1. So lambda is the volume fraction of the particle. So 1 minus lambda is the volume fraction of the fluid. So 1 minus lambda times h plus lambda times e. That's completely natural. And then in the left-hand side, you see you don't have the Laplacian, but you have some effective viscosity b bar, as we will be calling it. What is quite natural from the point of view of homogenization then is to have some kind of self-formula for the effective viscosity. So here I'm assuming that my ensemble of particles is stationary, so it's invariant under translation, and is ergodic, which is like the minimal assumption that we make in always in homogenization. And so the formula that you expect for b bar is just of this kind of form. So it's just like the infinite volume energy of some corrector, as we call it, psi. And so this corrector, the interpretation is like very simple. So you should just think that if you fix yourself a direction E for to compute the effective viscosity, so E is just some kind of trace-free matrix because everything is divergence-free, so it's just a trace-free matrix. So if you fix yourself E, you can look at the linear coordinate in that direction, EX. Of course, EX is divergence-free, so it satisfies the Stokes equation in the whole domain. And so now you define the corrector as exactly being the thing you need to add to this linear coordinate in order to have the Stokes equation in the whole domain together with the rigidity constraint. Right? So psi is just like the corrector is the correction you need to add to linear coordinates to satisfy your constraint in the whole space. And of course, you like psi to be a correction, so psi should be sublinear. So it should be much smaller than EX in the sense that it should be sublinear. So it's a very natural thing you want to define, right? Just like correcting linear coordinates to satisfy the different constraints. And more than taking it sublinear, actually, we are always able to construct psi such that the gradient is stationary. It's also invariant under translations and with expectation 0. So it's a little bit stronger than saying that psi is a sublinear. All right, so as usual, because all the problems here are actually variational, if I like, I can also write B bar as just the minimum of some energy of correctors where I minimize over the set of fields satisfying our constraint. So if you prefer. So the thing which is kind of new in this kind of qualitative homogenization result. So if you compare to the usual situation of a scalar elliptic problem like this, dv grad u equal f when you take like a oscillating coefficient, there are two important differences. So one is that here you have an incompressibility constraint, so you also need to deal with the pressure. It adds some difficulties. And then the other one is that, of course, you have rigidity. So you have it would mean essentially that you have a coefficient which is degenerate inside the particles. Right? So in fact, in this kind of setting, even in the periodic case, this kind of qualitative result was not known, which is quite surprising because it's a very natural problem, but strangely, it had never been considered. So now, is this theorem actually true? So in fact, there is no chance for this to be true. Because, well, you know that, so here I make no assumption on the set of particles, just assuming stationarity and ergodicity. But then you could imagine that all the particles are like touching and fill the whole space, but they all touch, right? And if that's the case, of course, because particles are rigid, it would mean that on the whole space, you would have something rigid because they all touch. So of course, you need to make some assumption that all particles are somehow not percolating and are not filling the whole space. So you have some key assumption. This is only true under some key assumption on interparticle distances. And this is why it becomes very interesting. So what most people have been considering in the past in this kind of the problem is always some kind of uniform assumption that the particles are uniformly far from one another. So there is like a uniform positive distance between all the particles. So if that's the case, you have a lot of space to make all your construction. It's not very difficult to prove homogenization in that setting. That's quite easy with a kind of a standard method. In particular, you can easily check that the limit B bar should be finite just because you have enough space to relax everything. So if you have a result under this kind of uniform assumption, then it's kind of natural also to try to relax it and just to assume some kind of moment bounds on the interparticle distances. And this is something you actually know in the scalar case. You know that you only have to make some logarithmic moments on the inverse of the distances. Here, you are not in a scalar case. It's actually much more complicated because you have the incompressibility constraint. And so the only thing you can prove is that you still have homogenization, provided you have this kind of moment condition, which is actually still quite strong, which are just moment conditions. So in dimension 3, it will be a moment of order 3/2 on the inverse of interparticle distances. So this is already much better than uniform condition. But then you must just ask yourself the question, well, under the dynamics, so is this kind of condition likely to be true? And I mean, if you look at like your whole microstructure, your particles, they are evolving. Of course, you know that I mean, they will only collide in infinite time, so they should not touch so much. But of course, they can be very close. And this moment condition, there is essentially even this moment condition, there is no real reason why you would expect this to be true. Actually, you don't expect this to be true along the evolution. If you look at the invariant measure, this would not be true. You would not have moments of order 3/2. That would not be true in dimension 3. So this is still something we'd like to improve. Otherwise, there is no way to couple with the dynamics. And also, if you think about what I was telling you, so the reason why you need such assumptions on distances in particles is that you want to avoid percolations of particles. So you could not. So if you just have two particles that touch, that should not be too much of a problem. So of course, when two particles touch, at the contact point, you have very bad control on like the pressure, on everything. But still, if you have two particles that touch, I mean, physically, you expect that this is just like a superparticle, and still, it would not matter for homogenization. And this is indeed the case. It's really not trivial. It's but you can also prove homogenization around under some kind of cluster condition. So you just look at sets of particles which touch or which almost touch, or which are at distance that is smaller than a given threshold, and you consider the corresponding cluster, and you look at the size of the clusters. And so what you would like to prevent is to have two big clusters. And so what you need is actually just to assume that the diameter of cluster has some bounded moments, and a sufficient number of bounded moments. And if that's the case, we can still prove homogenization. And so a technique, so I don't want to enter into the details of the proof of those homogenization results, but just so that you know, a technique, there is something very subtle here, which is that you need absolutely to avoid looking at what happens very close to touching particles, because there everything becomes quite degenerate and you don't have a good control of anything. And so the only kind of method that was working was to use some kind of variational technique based on gamma convergence, which essentially allows you to construct some black box for what happens inside the clusters and just look at what happens between the clusters, and which physically is very meaningful. And in fact, even in a scalar setting, proving homogenization in a degenerate setting under this kind of condition is actually new. I mean, it's really, okay, it's very close to what people were doing in discrete homogenization, where they also have some kind of just percolation condition under which they can prove homogenization. But in the continuum setting, this was really the first type of result. Right. Okay, so I just like to say this about homogenization to show you what are the different kind of conditions and what are the difficulties, and so the kind of conditions under which we can still prove the result. And of course, the motivation is to be able to talk about the dynamics, the evolution later. And I mean, this kind of cluster condition looks meaningful to couple. I mean, that it would be remain true in a certain way under the evolution of the microstructure. So there is some hope to do that. So let me just mention one more thing about homogenization. I mean, here we're just talking about qualitative convergence. Of course, we can always also try to prove quantitative results. And so you know that there have been a lot of techniques that have been developed over the last decade, let's say, to prove quantitative results, and we can actually adapt all that to this setting, and we get also like optimal rates of convergence for U epsilon. I mean, there are new difficulties, of course, mainly because of rigidity, which really giving some new difficulty, but in any case, it's working. I don't want to spend too much time on that. All right, so this is the first part about homogenization. And so now that we understand this notion of effective viscosity, we understand its definition in terms of the corrector, then let me turn to the second question, which is about trying to understand how this behaves in the dilute regime. So how we can make an asymptotic expansion of this object when the volume fraction lambda is very small. So this is actually a very a classical type of question in physics. So as you know, it's a kind of question that we're already considering in the 1850s by many people in physics. Essentially, it was the time when people were trying to derive phenomenological laws to describe the physics of continuous media. So they were always starting by looking at some discrete model, and then they were just like passing to the limit. Even actually, even Navier and also Cauchy were doing that very often. So they were like considering some discrete model and then trying to pass to the limit to get some meaningful equation for continua. And so this often led them to consider some homogenization problem. And what they noticed is that, of course, effective properties are typically, as we see here, very complicated to compute. It involves some kind of corrector and so on. But what they notice is that when you are in a dilute regime, you can compute first order approximations for effective properties, and those first order approximations are often explicit and can be very useful in physics. So actually for our problem of effective viscosity, it was first computed by Einstein, but really following this whole kind of techniques that were developed before to compute dilute expansions. And so what he computed is the following. So to leading order, of course, B bar is just like the viscosity of the plane fluid is just one. And you don't consider any particle. And then the first correction, and this is the usual thing that people were doing, is just to say, well, the first correction, because particles are very far from one another typically. So essentially, you just look at them as being isolated. And the first correction should just correspond to just summing the contributions of particles like being isolated. So you sum the one particle contribution. And if you do that, this is what Einstein computed here for effective viscosity. He obtained something which is then linear in the volume fraction of the particles, and you have some kind of universal factor phi, which is kind of beautiful. It's universal. Of course, it's not a fully universal. It depends on the geometry of inclusion, in the sense that this is the value for spherical particles. So if you have like ellipses, it would be of course different. All right. And then he postulated that the remainder is small. And of course, for us and more generally, actually, oh yeah, and I should mention, so that actually Einstein proved this, so it's really in line with what was done before, but he proved that in 1905 in his PhD thesis, and then he combined that with some other things to get an estimate on the Avogadro number. So in fact, this formula, he proved it just as a starting point for something extremely important, which was estimating the Avogadro number, and then discussing this atomistic view, the fact that the atoms, and so for physics it was actually something extremely important. But I should of course emphasize that this formula was just the basis for some very important physics argument. All right, so then in fluid mechanics, of course, there was a lot of interest about the error, because if you want to understand non-Newtonian effects, well, we saw that we see just that the first order, the first correction, Einstein correction, is universal. So you don't see any of the geometry here. So you still don't see any like non-Newtonian effects. Of course, the non-Newtonian effect should come in the next order term. And the next order term, like intuitively, you expect this just to be like sum of contributions of pairs of particles, because it's the first order is a contribution of one particle, then second order should be sums of two particle contribution. The thing is that because everything is long range, this kind of sum is completely divergent. And so it was very difficult to make sense of this kind of object. And it was first understood by Batchelor how to make sense of this divergent series, how to renormalize it properly. And he was then able to compute it at equilibrium. And then, of course, there is a question about next orders. And actually, for next orders, the renormalization is not that clear, and was not that clear in physics. I mean, physicists were writing down some kind of formal cluster expansion, but I have not found anywhere in the physics literature any argument on how to renormalize, how to make a sense to those objects. And this is something I will be fully discussing in the sequel. All right, so let me just emphasize the difficulties again. So there are two types of kind of substances. The first thing is that hydrodynamic interactions are multi-body. This is why you don't just have like contributions of pairs of particles. I mean, you need also to consider triplets and so on. And you need to make like a whole cluster expansion, a cluster estimates to say that you are approximately like you approximately just need to consider pairs and triplets and quadruplets, and the rest will be each time errors. So this is the first thing. And then the other thing is that all the sums that you will be writing down naturally are actually not summable, and so you require some renormalization. This is really like the long range character of interaction. So let me just tell you how much long range you actually are, and this is a small computation. So let me skip it, but you can easily see that if you look at the corrector and you add a point, you add a particle at a given location x. If you look at the difference for the gradient, in fact, you see that this is like the second gradient of a Green's function. So you see that it will decay in the distance to the observation point y. So it will decay like a minus d power. So of course, this is not integrable. This is why we say that it's long range, it's not integrable. But you see that still it's borderline. So it's not very far from being short range, right? So of course, it's not only the behavior at infinity, which is interesting here. So it's borderline, and also what you could say is that this is a bit cheating. Well, you know that the second one of Green's function, it's like a Calderon-Zygmunt operator, Calderon-Zygmunt kernel. So you know that to make sense of Calderon-Zygmunt integral, you should never put absolute values. You should, and you can always make sense of that, just in some kind of weaker sense. So of course, you are not absolutely summable, but still you can. Usual theory gives sense of everything. The only thing is that the quantities that we'll be considering, they're not just like one Calderon-Zygmunt operator. They will be like some very complicated combinations of Calderon-Zygmunt operator that are not even explicit. And so using this kind of trick is actually not really feasible in our setting, but this is of course what you should have in mind. In the end, what you want to do is to make sense of some kind of complicated Calderon-Zygmunt integrals, but which are not explicit, which will be the whole issue. Okay, so the goals then are twofold. So the first thing is that I would like to give a proof of Einstein's formula, Einstein's approximation. This is something that has been studied a lot in the last decade, actually. But there are many things that were not settled. In fact, there are two things that I would like to discuss, and for which we will obtain an optimal result. So the first thing is that you'd like to understand the error. So usually people are making very strong assumptions about the distance between particles, and like particles are very well separated to prove Einstein's formula, which is not very relevant physically. So you would like to understand exactly what are the minimal assumptions to be sure that this kind of Einstein's formula is true, that indeed the leading order is just given by this term 5/2. And so this is really about studying the error. And in fact, the error, according to physicists, it should be like quadratic in the volume fraction. So I would like to emphasize that. In fact, there is no way this to be true in general. This is actually not true in general. And so I just like to emphasize what should be the error and what is actually the optimal estimate you can get in the error. So this will be the first thing I will be discussing in detail. And then there is another thing that, of course, we saw that homogenization is possible to prove it under very weak conditions, like on clusters, on the size of clusters. And of course, we'd like also to prove Einstein's formula under similar kind of assumptions. So you'd like to have like a very robust proof where you can fit those different assumptions. So this is the first thing. And then once we understand Einstein's formula, of course, we'd like to understand all higher orders and to do this kind of cluster expansions rigorously and understand the different renormalization that are important. Right. So before I start with this Einstein's formula, I should, of course, the question here will be to understand the error. And so I would just like to tell you about cluster expansions and what size you expect for the different terms in a cluster expansion. Okay. So this will be the first thing I'd like to remark. It's kind of trivial observation, as you will see, but it's really important because it's I mean the result you get is non-trivial, and you really need just to think of it once. So you just consider some general function. So okay, so we'll be interested in B bar, which is the effective viscosity. But let me just to present the cluster expansion, let me just consider a general function of indices. So psi is just a function of the different points, and now I consider a subset of my set of points. So if you have a subset S, I write phi S for expectation of psi and just put the points in S. Right? And psi is just like any function of random function of your point process. So if you have such a function of indices, so you are interested, of course, in the function when you put all indices. So when you put the whole point process, so phi n. And in the dilute regime, you don't have so many points. So you want to say to leading order, it's just like phi of the empty set. You don't take any indices. So this is the first approximation. And then the next correction. So what is it? The next correction is about considering just one particle at a time. So you want to write it as sum over n. And then look at your function when you put one index or when you don't put any. So this is some kind of discrete derivative with respect to indices. I will denote it by delta n phi of the empty set. Then the next term is about considering pairs of particles. So you have now more particles. Of course, it's less likely to have to consider two particles at a time. Particles are quite sparse, so it should be like a higher order term. And so that's a sum over pairs. And then you look at what happens if I consider now a pair of particles, knowing that I've already considered what happens if I have just one particle. So this is now like a second order discrete derivative delta n. And this is a natural way to formulate cluster expansion, if you like. In this setting, and you notice that if you just have two points in total, of course you can then just truncate the summation here. You see that the phi n's just cancel each other, and you get just phi nm in total. So this is then just an identity. So if you're like an infinite set of particles, this is natural just to pursue this expansion to arbitrary order. So now, okay, so of course you'd like to apply this to B bar, to the effective viscosity. So this is also just the expectations of a function of your set of particles. So you just repeat this cluster expansion. So to leading order, you look at the corrector where you don't put any particles, which is then just 0. So you just have 1. So this is the leading order. Then the first term you sum over possible particles, and then you look at the expectation of your energy when you just put the corrector with just one particle. So psi is just you have one particle and you solve the corrector problem in the whole space. It's a one particle problem minus phi of the empty set, which is just 1 here. And so this is like delta n of this density plus then the second order derivative. I mean, so and you just write it down if you like for B bar. However, I just like to emphasize that all those sums here are not summable. So let me just show that. So even actually the first term is not summable. This is actually not a big deal for the first term, but as we will see. But actually, even this one is not summable. So if you look at delta n of the energy of the corrector, so you just expand the square. So you have a term which is linear in the corrector and a term which is quadratic. The term which is quadratic will have enough decay, so you don't care. But not the term which is linear. You have one particle at n. And you look, let's say, at 0. So this term will be, as we saw, you have a borderline decay. So this will be decaying like a minus the power of xn. And so, of course, this is not summable in xn. So this is not summable. And the double term, you see that here the second order term, you see that it's borderline decay in both directions. So again, this is not summable. we'll need to find a way to make sense of all those sums. But before we talk about that, let me just try to see what should be the scaling of the different terms. Right? So you expect the first term here to be of order lambda, then the second one, according to physicists, to be of order lambda squared, and so on. Right? So the question, so if we look in the physics literature, we see that the jth term in cluster expansion should be like a jth power of the volume fraction. Now let's see what we actually have. So if you just look at the first term, phi1, so just like the expectation, you sum over particles and you look at psi with a particle or without particles. So you have expectation of sum over particles. So just point process allows you to write this as an integral of your function with respect to the what we call the one particle density f1. And because you are stationary, of course, the one particle density is just like Lebesgue measure. You are invariant neutralization, and the parameter lambda in front is exactly the volume fraction or the intensity of your point process. So you have indeed you see that phi1 is of order lambda. Of course, provided that this integral makes sense, which is the case which is not the case in our setting. It's just the case if you have like short range interaction. But you see that at least formally phi1 should be of order lambda. So now let's see what phi2 should be. Well, phi2 now it's a double sum over pairs of particles of this kind of second order derivative of psi. And so an expectation of sums of pairs, of course, you write it as a double integral with respect to the two particle density f2. And well, so now what is the size of this integral? Well, I mean, the only thing you can say is that, okay, so again, provided that the thing here is integrable, this guy should be just of the order of the L infinity norm of f2. Right? I mean, you can't say much better than that. And so now this is the question. So what is the L infinity norm of f2 of the two particle density? So if you are in a Poisson setting, you have independence, and you know that the two particle density would just be like the square of the one particle density. So f2 would just be lambda squared. So in the Poisson setting, you have full independence, and indeed phi2 would be of order lambda squared. Now in the general setting, well, you just have like the L infinity norm of f2. I will call that lambda 2, which I will call the two particle intensity. And in fact, you can see that it can be anything between lambda squared and lambda. It can be actually as large as lambda. If you now have a point process where each time you have a point, you know that with property 1, you have another point to the right of it at a fixed distance. Right? So if you have such a process, then of course you know that lambda 2 will be exactly like lambda. Right? The two particle intensity will just be like the one particle intensity. And so you see that if you want to have the accuracy of Einstein's formula, you view this as just a first order cluster expansion. If you want a first order cluster expansion to be accurate, there is no other choice. It means that you would need the error, so you need lambda 2, the second order term, to be much smaller than the first order term. So lambda 2 should be much smaller than lambda, which is something non-trivial. So this is exactly the assumption that you would need, which is some kind of local independence assumption. You don't need to have really like a Poisson behavior. You just need to have a little bit of lambda 2 should just need to be much smaller than lambda. Right? So this is exactly now the condition. And so more generally, if you look at the jth term, it will be not like lambda to the power j, but it will be like lambda j, as I will call it. So that will be my j point intensity, which is just the infinity norm of the j point density. Right, so now we understand well, the size of the different terms. So now I can state our result on Einstein's formula, which with the optimal error estimate. And okay, so this is the form of it. So so b bar is like 1 plus the first cluster, the cluster of order 1. So b bar 1, we can actually make sense of this. It was given by a divergent series. In fact, we can make it convergent. I will explain it how just in a moment. And this is always of order lambda, as we are expecting. And in particular, for spherical particle, you can compute it explicitly. You get exactly Einstein's formula. And now about the error, you see the error. We expect this to be of order lambda 2, the error, as I was just explaining. And because you have just borderline decay, actually you don't have lambda 2, but you have lambda 2 times log lambda. And actually, this log is not just the proof which gives you that. Actually, it's optimal. So you can indeed construct, I will talk about that in a moment, but you can construct point processes where the error is exactly lambda 2 times log lambda. So this is really optimal. And we also have a result, as you see, when you just have like an estimate on the size of clusters. So whenever you can prove homogenization, essentially we can also prove Einstein's formula, the validity of Einstein's formula. And well, and then you see that the validity of Einstein's formula is provided that lambda, the size of b bar 1, is much smaller than the error. So what you need is that lambda 2 times log lambda is much smaller than lambda. So this is then the optimal condition to have validity of Einstein's formula. Yeah, and just a remark on b bar 1. So b bar 1 was given by this kind of divergence sum. And this was diverging because, I mean, there was also, there were two terms, both a linear term in the character and a quadratic term, and the linear term was diverging, was not summable at least. But the thing is that now you see, the linear term is essentially just the integral of a gradient, and the integral of gradient, if there is any way to make sense of it, it should be zero, right? So, and indeed, we show that in the limit, the proper way to make sense of b bar 1 is by removing this linear term, and just I mean, we just define b bar 1 as this quadratic term, and this gives you the correct term, and this is what you can indeed compute to be to coincide with Einstein's formula in the case of spherical particles. All right, so time is going on. All right, so let me still show you the proof of this formula, of Einstein's formula, because we have now a very simple proof. So I like it quite a lot. So let me just show you how it works. It's a very easy proof, in fact, just in one slide. So the proof is based on a variational ID. So you see that you know that b bar is just like the infinite volume energy of the corrector. So you can view that. So because particles are somehow far from one another, you can just consider like the cells around the different particles. You can construct large cells around each particle. Just take the Voronoi cells around the particles. So if particles are really sparse, then it means that the Voronoi cell will be very large, essentially. And so now this b bar, it's the infinite volume energy. So you can view that as taking the infinite volume average of the corrector on the different Voronoi cells. The corrector on different Voronoi cells. But now on a given Voronoi cells, of course, you have the corrector, which is taking all the particles into account, but you can compare it to a much simpler problem where you just consider the single particle, which is in the middle of the Voronoi cell, and you put at the boundary of the cell, you just put Dirichlet or Neumann boundary conditions. So this is very interesting because, well, b bar is the infinite volume average of the energy of the correctors on Voronoi cell, but on a fixed Voronoi cell, you can, of course, compare the energy of the corrector to the Dirichlet and the Neumann energy with a single particle. And of course, you know that the energy of the corrector should be larger than the Neumann energy. And just by doing some kind of cutoff, you see that also it should be smaller than the Dirichlet energy. So you see that b bar is between the average. So it's between the average, the infinite volume average of the Neumann and the Dirichlet energy of Voronoi cells. Well, now those Dirichlet and Neumann energy, they are kind of complicated because they are in Voronoi cells, so they're not in whole space. Of course, you'd like to compare them to the single particle energies in whole space, which is something that explicit. But now, similarly, you know that the single particle energy, so the integral of what I call the psi n, d psi n squared, will also be between the Neumann and the Dirichlet energy. So if you use all those bounds, these upper and lower bounds, you see that now if you compare b bar to the average of those single particle energies on whole space, you can just bound it by just the difference, the average of the difference between Dirichlet and Neumann energies. But now, when Dirichlet and Neumann energies satisfy the same problem, the only thing is that they just differ by the boundary condition. So, of course, when the Voronoi cell is very large, this should be very small. In fact, you can quantify that just using some elliptic regularity. And without any surprise, this should be just bounded by essentially the size of Voronoi cell to the power minus d. So what you have in the end is that you bound the error by just the average, the infinite volume average of the size of Voronoi cells to the power minus d. And now this is just by using a bit of probability. You can check that under our assumption. This gives you exactly lambda 2 times of lambda. And this is what we get. And you see that the proof is quite robust. So if you have different types of assumptions, like about the size of clusters of particles, you can just adapt this proof and you get the corresponding bond very easily. All right, so you see it's just like a variational approach. You just compare with Dirichlet and Neumann energy. So there is nothing very difficult. Okay, so this is great. This is about Einstein's formula. So now let's talk about higher orders. Higher orders, of course, the first thing you should do is to make sense of cluster formulas. And the thing is that cluster formula, they are like diverging series, so you'd like to make them converging. And of course, the natural way to do it is to start by some approximation. But you approximate b bar by replacing everything by the periodized quantity. So I consider periodic character, which I just solved the character problem now on a bounded cells of order L. And when the size L tends to infinity, of course, you recover b bar. Right? But now what is interesting is that for fixed L, you have a finite volume. You just have everything in a finite box. And then you have a finite possible number of inclusions in a finite box. everything is finite. So then you can just write down a cluster expansion, and now everything makes sense because you have a finite volume, so all the sums are actually finite. So this is great, but this is not what you want. What you would like to pass to the limit in this kind of expansion. So you'd like to show that all the B bar L's are actually converging to something, and that the remainder is bounded uniformly, and you'd like to have estimate uniform in L. So this is, of course, not that easy, of course. So if you want actually to first estimate the different B bar J's, L, in this approximation, so if you just do like brutal estimates, we saw that the cluster term of order J should be of order lambda J by the general kind of bonds that I showed you. And of course, the point is that you don't have something which is, I mean, you have some borderline decay in your integral. So of course, you expect to have like some log of the size of the box to some power. Right? So if you just do brutal estimate, this is what you get. And estimating the remainder is a little bit more complicated. I don't want to talk about it, but you can also do it. And essentially, you just get like lambda k plus 1, which is the correct order, times a certain number of logs. And you see it's a bit more complicated, but it really doesn't matter so much. So, I mean, this is interesting. You have the correct scaling in lambdas, but this is bad in L. So, of course, the question is, how can you avoid this L dependence? How can you remove this L dependence? And in fact, there is something you can do. And if you think that all those BJs are essentially like complete, so it involves differences of squares of correctors. So it's some kind of L2 based quantity, and it involves differences of correctors. And what I told you is that differences of corrector, you should view them as some kind of iteration of Calderon-Zygmund operators. Then because it's an L2 based quantity, you can believe me that there is some way to use just energy estimates because it's just L2 based. You just use energy estimate, and you are able to prove that the Jth term in the expansion is indeed uniformly bounded in L. So this is something that can be done just by using energy estimate. But of course, you see that this bond is uniform, that's great, but it doesn't give you the correct scaling in lambdas. And this is in fact unavoidable because, as I told you, the lambdas, they are defined as the L infinity norm of the particle densities, while the BJ, they are like Calderon-Zygmund operators involving also those particle densities. So if you want to make the L infinity norm of those particle densities appear, you would need to bound some Calderon-Zygmund kernel at some point in L infinity, which is not possible. So in fact, there is no way just by energy estimate to get the correct scaling in lambda J. Maybe you can get a small power, which is not even clear. I'm not even able to do that directly. But in any case, you will not be able to get, if you have some uniform bond, you will not be able to get the optimal estimate. All right, but actually, so those bonds could seem to be quite weak, but in fact, they are already quite interesting for the following reason. So essentially, the BL bar J, you should view them as being some kind of derivative. BL bar J should be somehow the J's derivative of B bar L with respect to the intensity of the process in a certain way. And so what this tells you is that B bar L converges. So you have a function that is converging to something. And then you know that all the derivatives are uniformly bounded. And so just like by usual thing, you know that then all the derivatives will also be converging. Right? So essentially, you just use this kind of argument and you can check that just those bonds will allow you to prove that all the B bar LJs then converge. So this is now very interesting because you see that those uniform bonds allow you to define the infinite volume cluster formula. So you can define them now as the infinite volume limit of your periodized approximation. Right? Those limits indeed exist. All right, so this is now interesting, but and you can even get something quantitative. So if for B bar L you have a certain convergence rate, you see that for B bar Lj, so the J term, the J derivative, if you like, you have the same rate to the power 2 to the minus J. So when J is very large, a priori the rate can become very bad, but you have some rate. Now, of course, the whole question is how can you, I mean, this is not enough, you can define a B bar J, but how can you prove that the B bar J are indeed of the size lambda J up to probably some logs, as we had for the error in the second term? How can you prove that? So essentially what you want to do is to go back to those brutal estimates where you have the correct scaling in lambda J, and you want somehow to beat this logarithm. But now you see that if you have some convergence rate for B bar Lj, when L tends to infinity, you can essentially hope to beat the logarithm if the rate is fast enough. So typically, if you have like algebraic rate of conversion, then you can just beat the logarithm. So this is, okay, so this is not the best proof, but at least this is like a huge shortcut, and it allows you to get a result in this way. So, so if you have an algebraic convergence rates for B bar L, then if you look at B bar J, because you also then have a convergence rate, which is just worth by a factor 2 to the J, but you also have a convergence rate for the Jth cluster term. Then just bonding B bar Lj with this logarithm, then you can just optimize in L and you get some estimate for B bar J, like lambda J times some logarithm. And we'll see that actually the number of logarithms is optimal here, as we'll argue just in a moment. And having a convergence rate for B bar L, this is actually something which we are able to prove just based on quantitative homogenization. If you have just some algebraic alpha mixing for the ensemble of particles, then you have indeed an algebraic rate for B bar L. So this gives you an easy result, just using a little bit of quantitative homogenization, that if you have algebraic alpha mixing, then you can control everything just by this kind of optimization. You can show that you can do the expansion toward the k. The error is lambda k plus 1 up to logarithm. The jth term is indeed for the lambda j up to logarithm. And you even have a convergence rate in the infinite volume limit. So this looks great. Essentially, you solve the problem to any order. But of course, there are a couple of questions. So one of the questions is that you have logarithm in the bound, so you'd like to know if it's optimal, and it's difficult to know whether it's optimal. It's just obtained here by optimization. It's kind of a cheap trick, but it's not really satisfying. So of course, one way to do would be to have a direct formula, infinite volume formula for B bar J, not just defining some infinite volume limits. So we renormalize, but we don't understand the renormalization explicit, just like some limit procedure. And then also we ask some algebraic alpha mixing, and we use some quantitative homogenization, which is not very satisfying because we just deal with the homogenized coefficient. So homogenization, quantitative homogenization should not play an important role here. So it's, for the proof, it's not very elegant actually to use that. So you don't believe that it's really necessary. Just a cheap trick to get a result quickly. So if you want to avoid that, and also there is the question of the convergence rate here, which is very bad when J is large, which is also not very natural. Actually, you expect to have essentially the same rate for all J. And if you want to understand all that, actually, everything just boils down to understanding renormalization explicitly, which is something we just did earlier this year to understand explicitly the renormalization. So to first order, it's very easy. I just told you that essentially you use the fact that the integral of a gradient vanishes to get a simple formula for B bar 1, as we had. To second order, okay, so this is then Bachelor's argument, which is now somehow classical. So you have a formula for B bar 2. You just notice that you can split it. You use another type of cancellation. I don't want to go into the details, which is this one, which is also a very simple cancellation. You can check. And this cancellation allows you to replace the two-particle density by the two-particle correlation function, which is just the two-particle density minus its value at infinity, essentially. And so because you subtract the value at infinity using this cancellation, you have some more decay. So you just have the correlation function, which if you have alpha mixing, this will be decaying. Right? So now you have a term which now makes perfect sense, which is perfectly integrable. So this is what was done by Bachelor to make sense of the second order. Another question is how you do that. Yeah, and so of course, just based on that, you can just look at this B bar 2. You can just look at this directly and estimate it, and you will see that it will be of order lambda 2 log lambda. And now you see where the log is coming from. It's exactly coming from here. You have essentially some Calderon-Zygmunt operator applied to the correlation function. Lambda 2 would be the L infinity norm of the correlation function. And so, of course, there is no way to bound in L infinity the Calderon-Zygmunt operator. And this is why you must have a logarithm. And actually, based on this formula, you can see that you can actually construct a point process such that this logarithm will be achieved. So that B bar 2 will be exactly of order lambda 2 times log lambda, just using the fact that you cannot have a bond in L infinity for Calderon-Zygmunt operator. That's it. And also by looking at this formula, you see that you have actually a very great bond on the convergence in the infinite volume limit, where the rate is just given by the decay of correlations. Right? So this is really optimal, and it saturates at 1 over L. So this is what you would expect to be optimal for the convergence. Now, what happens to higher orders? This is just to order 2, where you see you have simple cancellation that can be used. And in fact, to higher orders, you have no simple cancellation. There are not like a finite amount of cancellation that you can use to renormalize. And it becomes very quickly much more complicated. And in fact, what you need to do is to have a certain splitting of differences of correctors in more elementary terms. So here you just had like cancellation involving correctors. It's no longer enough. So you need to fully, so you have like differences, higher order difference of correctors. You need to fully decompose them in terms of suitable elementary terms. So I see my time is I'm a little bit over time. So let me just finish very quick with that. So you have some way to do some kind of diagrammatic expansion of differences of correctors. And at the level of those diagrammatic expansions, you will be able to capture some cancellations. So actually, it will not be exact cancellations, but just approximate cancellation in infinite volume limit. So it's even that is not completely easy, but you just reduce a couple of terms to boundary terms, and then you will have a couple of diagrams that will be remaining. And those diagrams then will be you just give you can just pass to the infinite volume limit, and they will just be given by summable integrals, and they perfectly make sense. So the thing is that you have like kind of complicated decomposition that need to be done. So for B4, for example, you have like 40 or 50 terms. So it's a lot. It's not very useful in practice, those formulas, but then you can use them to prove a much better result. So that indeed each bj is just bounded by lambda j times some logarithm. The number of logarithms is now proved to be optimal, and you have much better estimates for the convergence in infinite volume, and you can also estimate the remainder. And then you see that all this is without using quantitative homogenization, without using alpha mixing, but just some kind of decay of correlation functions. And well, so this is like much more satisfying. We really understand and what is behind those renormalization to all orders, and this gives you a much finer result, as you see. All right, so I'm already over that. So let me just stop here, and let me thank you for your attention.